Reynolds number, and it has closely associated with the interface flux. Hence, that is not discussed here when we are discussing convective flux, purely convective flux and molecular flux. Anybody has any difficulty? Okay, so we will continue our discussion. So today what we are going to do is we are going to solve some of the problem based on discussion on convective flux and total flux and molecular flux also. So that is what we are going to do. So in this series, so first is show that force per unit area, shear stress is force per unit area, can be okay interpreted as a momentum flux. Means how shear stress and momentum flux is one and same, or how shear stress can be called as a momentum flux, that you need to discuss in this question. So you can use the dimensions of shear stress, you can use the dimensions of momentum flux, and based on that and the definition of momentum flux and definition of force per unit area or shear stress, and conclude that force per unit area or shear stress can be discussed, can be explained, can be understood as a momentum flux also. Roll number 23, Kaushik.
Yes, sir.
Can you just explain this question, how to solve this question, and give your input?
Yes, sir. Like momentum flux means quantity, like momentum quantity by time by area, and force per unit area. By dimensional analysis, we can prove both are same.
Yeah. Can you just do it and just explain here?
Okay, sir. Sir, like momentum is mass into velocity. So
Hmm.
mass is kg, velocity is meter per second, and time is divided by time second, and area is meter square.
Very good.
So we get mass kg into we get kg per meter second square,
Huh?
and force per unit area. Again, it is Newton per
How
meter.
kg into meter per second square is how it is force?
Sir, like this is normal momentum flux, and now we are we are saying for force per unit area.
Huh. So
So
kg
now,
into meter per second square. What is that?
yes, sir,
What is
that is
that?
momentum flux unit.
No. Kg into meter per second square.
Kg into force.
Ah. Kg into force.
No, sir, kg into meter per second square is force. Newton.
That is mass into acceleration.
Acceleration. Yes, sir.
Okay, mass into acceleration is force. Force per unit area is a momentum flux. So very easy. So this is force. Shear stress is force per unit area, which is nothing but Newton per meter square. And force is nothing but the mass into acceleration. Okay, force is mass into acceleration meter square. So this is nothing but force per unit area. So this can be this is mass meter per second square. Okay, this mass can be kg. Okay, kg, and this is meter per second square is acceleration divided by meter square. This can be adjusted mass into meter per second. Okay, so mass into velocity divided by area into second time. So this mass into velocity is a momentum per unit area per unit time is a momentum flux. Hence force per unit area. Okay, so force per unit area can be interpreted as a momentum flux. Okay, so now this is exactly similar problem we have solved actually in during a discussion also. A Newtonian fluid with a viscosity 50 centipoise is placed between two large parallel plates separated by a distance 8 mm. Each plate has an area of 2 meters square. The upper plate moves in positive x direction with a velocity 0.4 meter per second, while the lower plate is kept constant. So lower plate, so here upper plate is moving in positive x direction. So lower plate is kept constant and is zero velocity. Calculate the steady force applied to the upper plate. so that we can get the velocity of upper plate equals to 0.4 meter per second. And then in part B, if the fluid in part A is replaced with another Newtonian fluid of viscosity 5 centipoise, if steady force applied to upper plate is same, now force applied per unit area or shear stress is same, calculate the velocity of the upper plate. In first case, velocity is given, so you need to calculate force. Using that force, change the viscosity and get the value of upper plate velocity. Roll number 38, Dayanand.
Yes, sir.
Yeah, so how to go for this? Which law is used here?
Uh, sir, I sir, sir, I just joined the meeting. I didn't read the question.
Today,
Yes, sir.
first time you are joining the meeting?
No, sir. Today it was late. I didn't remember that. Then,
Newtonian
uh,
fluid viscosity. Which law is related with this? Actually, viscosity, velocity.
sir, velocity, viscosity, Newtonian first law.
Newtonian first law. What is this that law? Newtonian first law.
Hello, sir.
Which is that law? Newtonian first law.
Sir, Newton's first law of viscosity, sir.
Uh, Newton's law of viscosity. What is that law?
Sir, uh, sir, for fluid mechanics, Newton's first law is like sir do like tau y of x will be equal to minus mu dvx by dy
Are you
constant
writing a
gradient.
notes, or just you are just listening to class and roaming here and there?
Yes, sir. Yes, sir. Writing the notes.
Okay, okay. Yeah, tell me.
Yes, sir.
So, how to solve this problem?
Sir, just reading the question, sir.
Yeah, roll number 56, Jitendra.
Yes, sir.
Yeah, how to solve this problem?
So,
Sir, can I tell you?
Yeah, tell me.
Sir, shear stress will be equal to viscosity into velocity gradient. Then shear stress will be equal to force upon area. We have
Uh,
given
uh,
that area will be equal to 2 meters square, and we have to calculate the steady force applied on the upper plate, and
yeah,
also given the viscosity.
yeah. Viscosity, and what will be the velocity gradient?
Velocity gradient, sir, we have to given velocity 4 meter per second, and distance will be equal to 8 millimeter.
Uh-huh.
So dvx by dy से velocity we can calculate velocity gradient.
You calculate that velocity gradient and tell me what is the velocity gradient.
Okay, sir. So just one second.
Yeah, roll number 56.
yes, sir.
You also calculate velocity gradient.
Yes, sir.
Everybody else also calculate velocity gradient. Roll number 77, Tejas.
Yes, sir.
What is
Sir,
velocity
50
gradient?
Hello, sir.
velocity
Sir,
by
38
distance
watt.
that is between the plate, which is
I'm whether I'm asking that definition of velocity gradient or value of velocity gradient.
I have
Can't you
calculated
understand what is going in a
4 by
class? You are telling me definition of velocity gradient.
Sir, 0.5 into 10 raised to power minus 3.
I am asking 0.5 into 10 raised to power.
Minus 3.
That
4
is the
by
velocity gradient.
Sir, velocity is 0.4 and divided by 8 mm.
Uh-huh.
0.5 into 10 raised to power minus
Minus
4.
10 power minus 4 or 10 power 4?
Yes, 4, 10 to power.
Yeah?
Sir, can I?
Yeah, tell me.
Sir, velocity gradient will be equal to 50. dvx by dv by dx will be equal to 50, and we can calculate f by a will be equal to velocity 50 50 cp दे रखा है, तो we can 1 centipi will be equal to 0.015 होता है, तो here we can calculate the force applied on the upper plate,
So
multiply
what
by
is
2.
force applied?
Sir, 5 Newton.
5 Newton. So everybody got this 5 Newton. Anybody is not getting 5 Newton can write in a chat box. Everybody not getting 5 Newton can write in a chat box. Anybody not getting 5 Newton can write in a chat box. Okay, now this 5 Newton is kept constant. Okay, 5 Newton is kept constant, and this fluid is changed now. Initially, it was more viscous fluid. Now it is less viscous fluid. Viscosity of the fluid is 5 centipoise only, less viscous fluid. Now you need to calculate the velocity of the upper plate, and lower plate is kept steady. Here, roll number
Sir, the velocity.
116, Abhijit, Abhineet. Roll number 116, Abhineet. Roll number 100, Ankur.
Yes, sir.
Yeah. What will be the velocity in part B?
So in part, sir, 1 second, in part A, we are getting 50 newtons.
50 Newton.
Yeah.
So have you written in chat box?
Yeah, sir.
Okay. How come you are getting 50 Newton? 0.4 divided by 8 mm equals to how much meter?
Sir, it will be a 0.4 divided by 8 into 10 raised to minus 3, no? Then it will be at 0.5 into 10 raised to minus 2.
Okay. And 50 centipoise equals to, you
50
need to
into 10
convert
raised
that
to
into SI unit, not poise.
yeah, 50 into 10 raised to minus 2.
Minus 2.
Into
This is what I have discussed actually. This is where most of the people will make a mistake.
sir, 1 Pascal into 1 Pascal into second equal to 100 centipoise, no?
You are asking me or you are telling me?
No, sir.
This is discussed in a class.
Yes,
You
sir.
should add
Point,
appropriately
point,
whenever it is told that if you understood. Once it is discussed in a class, then it is understood that now you learn. Now you don't
yeah,
ask me what is flux definition.
sir, point is CGF unit, no? Point is CGF unit, then
You
SI
are
unit will be
asking me or you are telling me? You should tell me now. This is not the thing. This is not the point to ask me whether centipoise is
sir, I'm not
CGS
asking.
unit or poise. Yeah, tell me. So how come
Sir,
you are
I'm getting
getting?
only.
How come you are getting 50?
Sir, 50 into 10 raised to minus 2
Hmm?
CG in SI unit.
Okay. And what is
And
the
then
area?
50 into 2,
2.
2 meters square.
And rearrange everything.
Yes, sir. 50 into 200, 100 and 10 raised to minus 2 to get cancelled. So remaining will be a 50 into 10, 0.5 into 10 raised to minus 2, which is 0.5 into 10 raised to 2, which is 50 Newton.
you are not doing correct unit conversion actually. Okay, you should revise everything.
Sure, sure.
Anybody else is getting
Yes,
50 Newton? Can you write in
yes,
chat
sir.
box?
Yes, sir. 50 newtons coming.
No, sir, it will be 5 Newton only.
Uh, uh,
Excuse me,
Because
sir.
velocity gradient
The
is
other
50.
persons, so the other persons are getting 50 Newton. They are converting from centipoise to poise. They should convert
That
into
is what I am
particles.
telling you. That is discussed in a class. That is discussed in a class. I know that where you will make a mistake. And this slide was discussed correctly actually. What is this here? Can you see the slide? This is SI unit. This is SI unit. So 1 Pascal second equals to 10 raised to 3 centipoise.
yeah, sir. Got it. Sir.
Got it? So this is you. I should give you Nobel Prize now.
No, sir, sorry, sir. Uh,
You are now in third year, and okay, it's fine that if something is not discussed, and I'm exactly pointing out everything where you will be making a mistake. So you are not listening carefully. Why I should discuss the unit of viscosity here? In Newton's law of viscosity, the unit of viscosity is so important, because I know that you people will make a mistake. That time I clearly told that. Okay, what is the relation between centipoise? What is the relation between poise? And what is the relation between SI unit and centipoise? Everything is discussed. And still you are repeating same mistake, means you are making a blunder now actually. This is not a mistake.
okay.
Okay, mistake can be made if you don't know the thing. If you know the thing and still you are making same mistake again and again, that is called as a blunder actually. You are not entitled to call you an engineer actually. You live beside chemical engineering. So what is this thing actually? Velocity?
4 meter per second, sir.
4 meters per second. Anybody is not getting 4 meter per
Meter per
second? Yeah, almost everybody is getting. Anybody getting any other answer? So this is the answer. Force is 5 Newton and velocity is 4 meter per second. Okay. This problem is also exactly similar. Only you can say they are adjusted some way. Okay. Input data is given in some other way. Three parallel plates are there separated by two fluids as shown in figure below. So this is the fluid with a viscosity 1 centipoise. This is the fluid with a viscosity 0.8 centipoise, and this is fluid A, this is fluid B, and this is moving with a velocity 2 meter per second in positive direction. This is moving with a velocity 1 meter per second in negative direction. So certainly there will be shear stress exerted by this plate in negative direction here, and there will be shear stress exerted by this plate in positive direction. So what should be the value of y2? Y2 such a that this plate will be a constant, okay, kept stationary. What will be the value of y2 so that middle plate will not move? It means that whatever be the shear stress, momentum flux exerted by this plate will be equals to momentum flux exerted by this plate. Okay, so you apply Newton's law of viscosity in this region. It will be mu a dv by dy, and this will be mu b dv by dy2. So v2 is given, v is 0, 0 and 1. This will give you dv, and dy is y2. Similarly 2 is given, and this is 5 centimeter. So y1 is given, so you can get the value of y2. Everybody got this idea to solve this problem? Anybody not understood the idea behind solving this problem? Yeah, roll number 85, Karthik.
Yes, sir. Understood.
Yeah. Can you give me value of y2?
Value of y2.
I request everybody to sit with notebook, pen and calculator in transport phenomena class. Don't attend the class from garden. Don't attend the class from football ground. Okay, you should sit like a class at your home or wherever you want to be and concentrate in a class only. And everybody should be with notebook, pen and calculator.
So y2 will be 2 centimeters.
2 centimeter. So
Yes.
can you just elaborate your calculation?
Yes, sir. Since the flux would be same, momentum flux would be same, then we can do dvx, that is velocity v2 minus the stationary plate. Say stationary plate is v2 minus this v1 upon dy is equal to stationary plate minus velocity of this third plate upon 5. So then we solve, we get 2 centimeters.
Roll number 116, Abhinit. Abhinit. Okay, if anybody is not answering, I am taking the granted that you don't need any mark out of 40. Okay, and you are feeling that you can score enough mark from remaining 35 plus 25 marks, remaining 60 marks to pass the TP. Okay, don't keep quiet. This is for everybody. So this answer is 2 centimeter. Everybody is getting 2 centimeter. Very good. No other answer. Very good. So this is the third problem. This I think you can solve it very easily. So heat transfer problem, conduction problem. So almost you might have devoted couple of units in heat transfer, solving more complicated problem. In fact, rather than this, here just to have a feel of Fourier law of heat conduction again. So so temperature is given. So you can use the fixed Fourier law of heat conduction. So it heat flux, rate of heat transfer divided by area, steady rate. That steady rate is given 72 watt. Area is given watt per meter square. That is equals to thermal conductivity into dt by dx. So temperature profile is given. How temperature is varying in x direction. But you can assume this is the actually glitch here. This temperature is distance measured in centimeter. So here if you calculate dt by dx, it will be a degree Celsius per centimeter. Okay, degree Celsius per centimeter, and flux is in watt per meter square. So you need to convert this into degree Celsius per meter and get the thermal conductivity value. That is only the point. Point to be remember is most important point to remember is this thing. Your unit of x here is in centimeter, and you want dt by dx in degree Celsius per meter. So appropriately do the unit manipulation conversion and use dt by dx, and you have flux 72 divided by 3 watt per meter square, and you can get the thermal conductivity. So what is the value of thermal conductivity? Roll number 83, Ishwari.
Sir, I'm getting 4 480, sir.
480. What is dt by dx?
Sir, 0.05, sir.
0.05.
Sir, no, sir. Sorry, sir. Sorry, sir. It is 500. It is 500, sir. K is 0.048, sir.
Anybody? What is the unit of K?
Sir, K is watt per meter Kelvin, sir.
Okay. So now you have converted degree Celsius into degree Kelvin.
No, sir.
So how come you got K in degree Kelvin? First of all, do you need to convert this degree Celsius into degree Kelvin?
No, sir.
Why? Why you don't need?
Sir, because that is as it is given in the form of expression, no, sir.
No, it is given in a form of expression, but this is in degree Celsius, na?
Yes, sir.
So why this degree Celsius need not to convert to get the thermal conductivity into degree Kelvin? Yeah, anybody else in the class?
So maybe because even if we convert it in Kelvin, then a constant value would be added, and when we calculate dt by dx, the constant will anyway get eliminated on
Yeah,
differentiation.
yeah,
So it will
because
not cause any
because
difference.
here we are not discussing absolute temperature. It is a delta T gradient we are discussing, and the unit conversion from Kelvin to degree delta T. A unit of delta T in degree Celsius and degree Kelvin is same. Unit of delta T, temperature difference. Okay, temperature difference. The value of temperature difference remains same. If I am considering degree Celsius or degree Kelvin, delta T. Here I am not discussing absolute value of temperature. That is why need not to consider. So what is the value of K you are getting? Anybody else? What is the value of 480? So some people is getting 4.8, some people is getting 480, some people is getting 0.48. So roll number 91, 480. How come you got 480? 91?
Sir, I did a unit calculation mistake.
Okay, this is what you will do every time actually. While joining chemical engineering also you have done a name calculation mistake. You want to join a computer science, but by mistake you join a chemical engineering.
No, sir, I want to join chemical engineer only.
Oh, very good, very good. Then somebody got 4.8. Roll number 99. Siddesh,
Yes, sir.
how come you got 4.8?
So calculation, unit mistake.
Very good. So I will also do mistake, giving FF grade to at least 10-15 student. Okay. So now solve this. This is very easy. Thermal conductivity is given, delta T is given, and delta X is also given. Area is given. Determine the steady rate of heat loss, rate of heat transfer. First get the flux multiplied by area will give you rate of heat transfer. Flux equals to K into dt by dx. Again here actually, this is the, there will be something actually, some important point or some glitch will be there in every problem. Sometime in exam, some easy question is asked, so you should look for this kind of glitch. Okay, because here the distance is measured in centimeter. Actually distance is given in centimeter and thermal conductivity is given in SI unit. All other thing are in SI unit. Delta T doesn't matter. So certainly this need to be converted actually. That is what you should appropriately and exactly point out where the loopholes are there. There will be some loopholes while solving the problem. So what is dt by dx here? Your roll number 68, Mitu.
Yes, sir.
Yeah. What is dt by dx?
So sir, first 30 degrees Celsius, then minus 5 degrees Celsius, then upon 20 centimeters is there, so we will convert it into meters. So we will get.
I'm asking value. What is dt by
Yes, sir.
dx?
Yes, sir. Yes, sir. Sir, we will get dt by dx. We will get, sir, 175, sir.
Okay. So 175.
No, sir. No, sir. No, sir. Yes, sir. 35 divided by 0.2.
Yeah, roll number 38.
Yes, sir.
How come you got 500?
Sir, temperature difference will be equal to x equal to 0 pe temperature will be equal 10 degrees Celsius, which will be equal to 283 Kelvin, and x equal to 7
Where
centimeter.
is 0 degrees Celsius?
0, no, sir. X equal to 0. Hello, sir.
Where you are x equals to 0?
The thickness of the plate, then the one side of the plate, na sir. X
So
equal to
once
0 to
this it is given, na, inner and outer surface is given, na. Inner side is 30 degrees Celsius, outer side is minus 5 degrees Celsius. Where is 0 degrees
Sir,
Celsius?
sir, this one, no, sir. I am talking about last question. The answer will be equal to
Okay.
0.048.
How about
Okay,
this?
sir.
How about this? So this is 3150 watt. Everybody is getting this? Anybody getting any other answer? And already this is informed to you. So Saturday's class will be every week. Every week Saturday will have class from 11 to 1, 2 hours class, because this is what will happen whenever this is kind of tutorial, kind of revision and everything. So it will take a time. So I need to make sure that everybody is getting something at least. So it will be very slower. So certainly that tutorial will be of 2 hours class, and whenever it is there regular tutorial, this class you can consider as a tutorial. But when we'll go to shell balance and all, so that 2 hours will be used for specific tutorial. Now we'll conduct in regulation with in regular with a class. We will have some kind of tutorial like we are having today. Okay. So now this is important. Now here a little input is needed. That's all. Little input, not more. Energy generated uniformly. Energy generated uniformly. The thickness of wall is 6 centimeter. A temperature distribution is given. Temperature distribution is 145 plus 3000 Z minus 1500 Z square. Temperature is in degrees Celsius and Z is the distance measured from Z is measured in meter. Okay. Determine the rate of heat generation per unit volume. G. You might be remembering G. Rate of heat generation per unit volume. If thermal conductivity is 15 watt per meter Kelvin. Thermal conductivity is given 15 watt per meter Kelvin. So what will be the rate of heat generation per unit volume? Can anybody give some idea how to solve this problem? A little input is needed, and this is also already you have covered in a heat transfer. And you can get it from Fourier law of heat conduction. Hint is only Fourier law of heat conduction is more than enough. Yeah, anybody in a class? Yeah, roll number 1, Abhinav. Yeah, can you give some input?
Sir, we can calculate temperature gradient first.
Yeah, delta T by delta X or delta Z here.
Sir, then we will put the value of Z, that is 6 centimeter in that.
Okay. We want rate of heat generation per unit volume.
Yes, sir. So here in equation Qy is per unit area, na? So for per unit volume, we will divide it by 6.
Okay.
6 centimeters.
Divided by 6 centimeter.
Yes, sir.
Okay. How you will get the area? What is the area?
Sir, here heat is per unit area, no?
Okay.
So we
So
need per unit volume. So
okay. So can you just calculate and let me give me value? Roll
yes.
number 2, Abhishek. Yeah.
Hello, sir.
Yeah, tell me.
Hello.
Tell me. I'm able
Yes,
to
sir.
hear you.
Yes, sir. So we know thermal conductivity 15 and dT by dz will calculate, and A is given as unit area, so it's 1, and dT by dz would be 3000.
So that is heat generation per unit volume, na? Volume should be also 1.
Yes, sir.
If area is say 1 meter square divided by 0.6 or multiplied by 0.6, you will get 1 meter square.
Sir, can you repeat it?
If I'm dividing it by 6, so whether area will be unit
No, sir.
volume.
We'll take Z as 1 centimeters.
Z as 1 centimeter. If Z as 1 centimeter, then rate will be equals to heat generation. Roll number 24, Bandi.
Yes, sir.
Yeah, can you give some input? This is why you should not treat mathematics as a pure mathematics. Okay. So you have studied mathematics, that to apply in a chemical engineering. So, but unfortunately, when you are studying mathematics, you was not knowing chemical engineering. Now you want to study mathematics and you forgot you want to study chemical engineering and you forgot all the mathematics now. Yeah, anybody else in the class can give any idea? Yeah. Roll number?
So roll number 6.
6. Yeah. Can you tell me?
So we need energy generated per unit volume.
Very good.
So heat flux is already energy generated per unit area.
Okay.
So, sir, the dy term which we are in the formula when we use qy equals to minus k dt by dy. So, if we shift the dy this side, then it would be area into dy. That would be the volume of the entire brick. Area
Okay.
into the dy. That
So
would be the
what is dy? What is dy then?
So, dy is the distance, sir. This distance which we are having.
6 centimeter.
Sir, we need not to put it whatever it would be. It does not matter, no, sir. If area into the distance, that will make the whole brick.
So you mean to say rate of heat transfer?
Yes, sir. Yes, sir. Per unit volume would be equals to K into dt.
Okay.
And sir, now,
what will be the value then?
Sir, K value we are having 15 watt per 15. We are having the K value, and sir, the T value we can calculate from the two. So we need dt. So dt would be T value at x equals to 6 minus T value at x equals to 0. So we can get dt from there.
Okay, but that will give you wrong answer. That is what I am telling. Okay, let me see. Okay, this is what happening. Okay, this is the rate of heat transfer. Okay, consider a slab of differential thickness delta y. This is not 6. This is differential thickness, and thickness is delta y, and delta y is a smaller. So here rate of heat transfer is qy. Here rate of heat transfer is qy plus delta y. Q at y plus delta y. This is the, you can say, rate calculated at y, or flux calculated at y, and this is the flux calculated at y plus delta y, and A is the area, surface area. Is the surface area. Now I can take the heat balance. What will be overall heat balance? Input, rate of heat input minus rate of heat output plus generation. This is what I am interested in. Minus consumption plus accumulation equals to 0. Here consumption is 0, accumulation is 0 because it is steady state. As it is steady state, accumulation is 0 and consumption is 0. So input minus output equals to generation. Okay, rate of heat input minus rate of heat output equals to generation. I want generation per unit volume. Okay, this is generation, rate of heat generation. It is not per unit volume. This is generation, and this is rate. This is also rate. So everything will have unit of energy per unit time. That's all. Okay, this is not an input. This is not a per unit area. This is not. This is rate. Okay, this is rate. So rate of heat coming in this differential shell will be qy into A. This is what rate of energy coming in, and what is the rate of energy going out? That will be q flux estimated at y plus delta y into area. This will be a rate. And this generation, if G is a heat generation per unit volume, capital G is a heat generation per unit volume multiplied by volume. So volume of this differential shell will be area multiplied by delta y. That will be equals to 0. Now rearranging this equation, so what I will get? G will be equals to flux at y plus delta y minus flux at y divided by delta y. When delta y tends to 0, I will get a differential equation. Heat generation will be d by dy of qy. And qy I can get it from Newton Fourier law of heat conduction. So certainly qy will be equals to minus k dt by dy. Okay, qy equals to minus k dt by dy if dt by dy is negative. If dt by dy is positive, this will be positive qy. Now substituting here, so what I will get? Rate of heat generation per unit volume. This will be rate of heat generation per unit volume will be minus k d2t by dy square. Now double differential of same equation d2t, double differential of temperature profile multiplied by thermal conductivity with respect to y, that will give you a rate of heat generation per unit volume. Everybody is getting this heat generation per unit volume, and this you have covered in heat transfer. I'm sure, I'm very much sure that this you have covered. heat generation per unit volume equals to minus k d2t by dy square. Roll number 34, Dhiren.
Yes, sir.
What is the value of heat generation per unit volume?
Sir, doing, sir. Just a second.
So now G will be equals to minus k d2t by dy square. That all depends upon now. Get the value of d2t, double differential of this with respect to z. There it was y. Now this distance changed to d2t by dz square. Whether it is positive or negative. Yeah, Dhiren.
Yes, sir. Double differential will be minus 3000, sir.
Minus 3000.
Yes, sir.
So multiplied by thermal conductivity minus 15.
Minus 45 into 10 to the power 3, sir.
45 into 10 power 3. So 45 kilowatt per meter cube. Everybody is getting this? Anybody getting some other answer? Minus 3000. Yeah, 45,000. Yeah. Anybody has any doubt in this problem? Now in continuation with the same problem. Okay, in continuation with same problem is instead of this temperature profile given in the form of equation, this can be given discretely. This can be given discretely. Temperature at different points can be given discretely. How to handle that? Same problem. It is same problem. This problem and this problem is same. Okay. Here also you need to get the heat generation per unit volume. Here also you need to get the heat generation per unit volume. Here what is the here temperature profile is given, model equation for temperature profile is given, while here a discrete value of temperature is given, discrete at z equals to 0, 30, so z equals to 0.1, 45.8, this thing, this thing, this thing, this thing. So and you need to do same thing, and heat generation per unit volume will be minus k d2t by dx square. How to handle this problem? Yeah, Abhinit. Now your mic is working.
Yes, yes, sir.
Okay, now tell me how to handle this problem.
So we will make a graph, and from the graph by interpolation we can relate between t and x.
Okay.
And sir, there is a one more method, sir, we can apply here. That difference, sir,
Very good.
whatever the heat got generated, it will flow either from z equals to 0 or z equals to L, because sir we have neglected the x and y term. So we can also find q at x equals to 0 plus q at x equals to 0.6, and if we will divide it by area, we can got the heat generated per unit volume.
Where is the area actually? Area is not given. Na?
So area can be area of cross section into the thickness, and q will be minus k a dt by dx. So a got cancelled and we will get that thickness only.
Okay. So that will give you wrong answer actually. That will give you wrong answer. Your first analysis was correct. You can fit the value t as a function of z. You can fit all the values and get the temperature profile. Then this will be, you will get a similar equation like this.
So the other I was explaining for the previous question.
Okay. So now that is wrong actually, fitting this and getting model equation for z and then getting double differential. Do you know how to get the discrete differential value from discrete values? Differential values from discrete values. So using this, I can get dt by dy. Okay, delta t by delta y. Here also I can get delta t by delta y. So d2t by dy will be delta 2 delta t that difference divided by dy square.
So delta t upon delta z plot versus z, and that slope will give me d2 t by dy square.
Okay, so that is intermediate. Okay, that is intermediate. What I am telling is easier way. Okay, so this is k minus k d2t by dy square, that will be equals to minus k delta 2t by del y square. How to get this value discretely? So this is t, this is y. You get the value of delta t, you get the value of delta y, and this is delta t by delta y. So delta t by delta y, and this minus this divided by delta y, you will give delta 2 by delta y square, and you can get the average value. You can get the average value, and that average value multiplied by thermal conductivity will give you a heat generation per unit volume. Everybody got this? How we are solving this discrete differential, double differential, in fact not differential, double differential. Here roll number 49, Harshvardhan. Switch on your mic.
Yes, sir. Can you hear me?
Yeah, I can hear you now. Tell me. So, do you got this? Do you got these values?
I did not understand how you got delta 2. The last step I am stuck, sir. I am going to
Here.
No, after that.
So dt by dy. So this will
I got
be t2 minus t1 is dt. y2 minus y1 is dy. So dt by dy. Similarly, you can consider this at y1, this at y2. So this minus this divided by y2 minus y1, that will give you d2t by dy square. This you might have done so many times in least square method, in numerical method actually. While fitting the equation, getting all these constant values and all. So K, yeah?
It's coming 2.4.
2.4. Let me see. These are the values. Okay, I don't have values actually. Don't have values. The value is 1920 watt per meter cube. Anybody is getting these values? Anybody? Anybody getting these values?
Sir,
Yeah.
yeah, I'm getting like comparing 0.1 with 0, x is equal to 0.1 and 0. I'm getting the slope as 158. Then for the second one, I'm getting 110. And after finding the difference for dt square by dx square, I'm getting the value as 24. 24 divided by 0.2, which is...
Look, this is T. Can you see my screen? Can you see my screen?
Yes, sir. Yes, sir.
Yes, sir.
Okay, this is Z. Okay, this is Z. Oh, this is temperature and this is Z. This is Z and this is temperature. So now I should go insert symbol delta. Yeah, delta. This is delta Z. delta T. So what are the values? Delta Z will be a this minus this. Okay, this is delta Z. So delta Z is constant. Okay, delta Z is constant. 0.1. So what is delta T values? This will be a 45 minus 30. Okay, this is delta T. Okay, everybody is getting this value. Now think that this is delta T value at this thing. Okay, dt by dz. Okay, dt by dz will be a dt by dz. That will be equals to this delta T divided by delta Z. 158. This is what you are getting. Yes? Anybody?
Sir.
Yeah. So now this will be actually dt by dz divided by delta z now. So this minus this divided by this minus this. Okay. So this d2t by dz will be a, so you can consider this at y1 equals to, this will be a delta 2 divided by again this minus 240. Everybody is getting this? You should get this multiplied by 8. What is the value here? Thermal conductivity is 8. So this will be a average value is 240. So 8 multiplied by 240. 1920 watt per meter cube actually. This is what answer is. 1920 watt per meter cube. So this is d2t by dz square. What these values? Everybody? Okay, we will stop here. We'll continue in next class. If you have any doubt in this problem, so we'll discuss at the start of